next we're going to talk about Dalton's law. So Dalton's law says in a mixture of gases, the total pressure is equal to the sum of the partial pressure of each gas. So we can see here that gas A's pressure is 1 atmosphere, gas B is 2 atmosphere, and gas C is 1/2. So if you add all those together, you get 3.5 atmospheres. The best example of this is air. So air is something that we're constantly breathing in, and how much, based on our ventilation chapter, we're exchanging on average about 4 liters per minute. And that's an average of all the population of how deep, so our tidal volume, and how fast our respiratory rate. So the air mixture is nitrogen at 78%, oxygen at 20.95, or we're just going to say 21%, argon and carbon dioxide, and there's other gases also that are very small amounts. So mainly it's nitrogen and oxygen. And we already said that at atmosphere, 760 is 759, 760 is in millimeters of mercury is the atmospheric pressure. Well, that's mostly made up then of nitrogen. So if you look at 78% of 760, that's where you're going to get that 593, or 21% of that 760, that's where you're going to get that oxygen pressure of 159 millimeters of mercury. So here's another example. We have oxygen and nitrogen together to make up the partial pressure or the total pressure in atmosphere of air. And that's approximately 760 at sea level. Now here we are. We are learning respiratory therapy in Denver, so we have to talk about altitude and oxygenation. So at sea level, we said the barometric pressure is approximately 760 torr, or millimeters of mercury, same thing. So therefore, 21% of that, which is what is the percentage of oxygen in the air. So once again, if we take our calculators and we say 760 times 0.21, because we're looking at a multiplying by a percentage. So we can't just say 21, we're saying 21%. So we have to multiply by 0.21. So if we go 760 torr times 0.21, which is the percentage of oxygen in the air mixture, we get approximately 159 torr. Okay, so from that table, that's how much pressure of oxygen is in our ambient air. Okay, so let's see what happens when we ascend in altitude, meaning when we go up. So as you can see here from this chart, as the altitude goes up, the barometric pressure goes down. And because the percentage of oxygen in the air mixture doesn't change, our oxygen also goes down as we go up in altitude. So let's look here. Here in Denver, we're 5280 is our sea level. Here in Aurora, we might be maybe a little bit higher. So let's just say we're at 6,000. So you can see here at 6,000 feet, and that's 1830 meters, our barometric pressure is only 609. So if we take our calculators and we say 609 torr times 0.21 percentage, we calculate that up times 0.21, and we get 127, okay, 0.8, 127.8, okay, so that's millimeters of mercury or torr. So as you can see then, if we look at our alveolar, we're always having diffusion, so now the oxygen pressure in our alveoli is down to 75, where it should be up there at 105, over 100. So we're really, and then if you look at our saturation, which is the amount of oxygen that's attached to hemoglobin, we're really low here in Colorado. And as we continue on, we'll talk about ways that we do acclimate, but just know that we are always at a disadvantage here when it comes to oxygen. So that can really be a problem for people with chronic lung or heart conditions, because if they're already hypoxic due to the problems of the lungs or the heart, it can be even worse here at altitude, up here in Colorado. So if you've ever visited Vail or Steamboat or Leadville, they're much higher. So if you ever drive up there and then try to exert yourself, like going hiking or biking or running, you'll notice that as you continue to go up, the oxygen pressure is so much lower, you get sick. So you might feel like you have a headache, a stomach ache, you might just feel worn down, and that's because you have less oxygen. And then, of course, if we go hiking in the Himalayas, their altitude can get up here closer to 25,000 feet. And if you look here, this is classified as moderate hypoxemia to even start with. So in that case scenario, it would be in the ambient air, this would be in your alveoli, and that's considered severely hypoxemic. So those people have to wear oxygen, or they're just not going to be able to even function and use their muscular strength, because it's just too much of an anaerobic environment, meaning a low oxygen environment. So just for some background a little bit, dissolved gas in a solution exerts a pressure that it's called a tension of that gas, and it's denoted with a P. So when you keep seeing P, that means pressure. Then, so that's PaO2 or PCO2. Then when we have the next letter, when we have a small a, that means an arterial blood solution. And if we have a big A, that means alveolar. So little a arterial, big A alveolar. So when we're looking at our FiO2, or our fraction of inspired oxygen, oxygen is 21% of the atmospheric air at sea level. So that's 159 PaO2 of oxygen at sea level. Now, one thing you need to remember is, even though as we ascend into altitude, our pressure goes down, but our FiO2 does not change. We always stay at 21%. Our final equation that we're going to look at is our ideal alveolar gas equation. So that's our P big AO2, which is alveolar. That's equal to our barometric pressure minus our water vapor pressure multiplied by our FiO2, and that is all subtracted from our PaCO2 times the respiratory exchange ratio. And that's looking at our tissues, how much they uptake and consume of the oxygen versus how much carbon dioxide they put out based on our metabolism. Here's our equation. Let's do an example. So here it says, if a patient is receiving an FiO2 of 24%, that means they probably have a nasal cannula on at 1 liter oxygen. So that's just a little bit above room air, but so they are getting some supplemental oxygen therapy. On a day when the barometric pressure is 755 and the PaCO2 is 55, what is the patient's alveolar oxygen tension? So our P big AO2, so that's our alveolar pressure. Okay, so it's barometric pressure, 755 millimeters of mercury, minus our water vapor pressure. So if we're talking about inside our alveoli, that's always going to be at body temperature. So at 37 degrees, which is body temperature, our water vapor pressure is always going to be 47. Okay. This then is going to be multiplied by our FiO2, which here is 24%. Once again, we talked about a percentage. We have to multiply it by 0.24 to convert it from a percentage to a decimal. On a day when the barometric pressure is 755 and the PaCO2 is 55, and that's in torr, times 1.25. So now just looking at order of operations, we need to multiply this first, and we need to multiply this also as a unit, and then multiply the FiO2 times this, and then subtract this. That's your PEMDAS, just your multiplication. So 755 minus 47, we've already put here is 708. So 708 times 0.24 equals 169.92. Now we're going to subtract out that 55 times 1.25, and we get 101.2. We're just going to say 101 torr. So that is the pressure of oxygen in our alveoli. And that's actually within normal limits. So a couple of things here. The patient is getting oxygen therapy, but the patient's CO2, and we'll talk more about this later, is supposed to be at 40 torr, and this patient is holding in carbon dioxide. So they're up to 55 torr. So you would think this would be lower because you're subtracting this out. But because they're getting supplemental oxygen, their alveolar level is coming back to normal limits. And that's what we want to do for patients. Okay, we'll do another one. If a patient is receiving an FiO2 of 28% on a day when the barometric pressure is 740, and if the PaCO2 is 60, what is the patient's alveolar oxygen tension? Okay, so this is equation 2. So we're going to say 740 minus 47 millimeters of mercury times 28%. So that would be equivalent to putting a patient on a nasal cannula and giving them 2 liters of oxygen. Minus PaCO2 of 60 torr times our respiratory exchange ratio. And of quick note, you can multiply this by 1.25, or a lot of times you'll see it divided by 0.8, and that's the same mathematical number-wise. So 740 minus 47 is 693 times, or 0.28, which is 194, minus the 60, which we said is only supposed to be 40, so this is pretty high. 1.25, and we get 119. Once again, that is higher than normal because here we're giving a lot of supplemental oxygen. So barometric pressure has a lot of influence on the alveolar oxygen pressure. So once again, as we ascend into altitude, which we are here in Denver, we start out with a much lower barometric pressure, so that will significantly reduce the alveolar pressure.